Hi everyone, I'm Isiki from FKE UTHM. So in this video, I'm going to show you the solutions for the final examination semester 1 session 25-26 for the subject EMT. Okay, so question 1 we have go through just now. So this is question 2. Okay, so question 2, for the first one, you have to write the formula. Just write the formulas of Biot-Savart's law and Ampere's law. And B is differentiate between a magnetic field line and also the electric field line. Yeah? Okay, so for the question A is a very straightforward question. You just write down the formulas. Okay, so for Biot-Savart's law, okay, so it says that the magnetic field at a position P, okay, is proportional, okay, to the magnitude of the current and also the length, right, and also the angle that the length met with the distance r. Okay, so this is the cross product between the dl and r, and it is inverse proportional to the r square. Okay, so this is the Biot-Savart's law in integral form. And for the Ampere's law, okay, it says that if we integrate the magnetic field, okay, in the tangential directions, okay, in a closed loop, okay, we'll be able to get the total current that is enclosed by the loop. Okay, so this is a solution for question A, very straightforward. And for the question B is asking about differentiate between magnetic field line and also electric field line. Okay, so let us see what is the magnetic field. Okay, so magnetic field is come from what? Okay, it's come from magnet bar, right? Okay, magnet bar, and also come from the current filaments, right? So you can draw the magnetic fields around the current filament and also the magnet bar. Okay, so for magnet bar, okay, you have a north pole and you have a south pole, right? So the magnetic field should be from the north and go to the south. Okay, so this one should be the directions, right? So you can draw magnetic field lines, right, according to a diagram. Okay, so this is the magnetic field. And if the magnetic field is generated by a current, for example, this is the currents. Okay, so you can draw your magnetic field in this way. If this is the I and this one will be your H. Okay, so this is the magnetic field line. Okay, so for the electric fields, okay, so for the electric field, so electric field, they are coming from charge, right? They are coming from charges. So you can have negative charge, you can have positive charge. Okay, so if negative charge, okay, your electric field will be inward, right, surround the negative charge. And if it is positive charge, okay, the electric field, okay, will be outward, right, outward. Okay, so this one is when we consider these charges separately, so I don't put them together separately. Okay, so if I put them together, okay, so the field lines for the positive charge would seems like terminate, okay, at the negative charge. Okay, you can draw it this way, right? You can draw this way. Okay, and this one. Okay, so this is the electric field line, okay, from the charges, okay, and you can see the electric field line, okay, they start and also the end on the charge. Okay, you see the start and end on charge. Okay, and unlike the magnetic field, okay, so the magnetic field is converse. Okay, it's converse means that it stop at itself. Okay, start and stop at itself. Okay, so converse. Okay, so this is how you draw the magnetic field line and also the electric field line. Okay, so for question C, you have a circular loop. okay, of radius 0.1 meter. So you have a circular loop, okay, circular loop, okay, and the radius is 0.1 meter, and it carry currents of 2 amperes. So you have to find the magnetic field, okay, at the center, at these positions. Okay, so you can apply the Ampere's law that we write down just now is equals to integrate I dl, okay, cross unit vector r over 4 pi r, okay, over 4 pi r, okay, 4 pi r squared, 4 pi r squared, right? Is r squared, right? R squared. Okay, so this one is the directions. Okay, so we will put the direction aside. Okay, we just focus I and also dl. So if we integrate, the I is 2, dl is the length of the wire, so we can represent the dl using cylindrical coordinate system. Okay, r dv. Okay, r dv, and then we have 4 pi r. Okay, r is the distance, okay, between the wire and also your observation point. So it is actually following the dimensions of your radius, which is 0.1. Okay, so the interval for the phi will be 0 to 2 pi is 360. Okay, 360. So you can do this. Okay, so replacing the value of the radius, which is 0.1. Okay, this is 0.1, so you can replace it 0.2 dv, 0.2 pi, and then we have 0.4 pi. Okay, so let's calculate, integrate 0.2, 2 pi. Okay, so over here I have 2 pi over 5, okay, divide with 0.4 pi. Okay, divide 0.4 pi, which is equals to 1 ampere per meter. Wait, I missed this one. Is 0.1 square. 0.1 square, so this one is not going to be this. Okay, so 0.1 square, you have 0.04 over here, 0.04 pi over here. So your answer is 10 ampere per meter. Okay, is the magnetic field at the center of your loop. Okay, for question D, you have a semi-infinite filament wire. Okay, it lies on the positive y-axis. So let's draw this. Okay, let's try to imagine how does the lines looks like. Okay, so it lies on the positive y-axis to the origin. Okay, so from infinity to the origin here. Okay, so this is your wire. Okay, right, and the current is in the negative y directions. Okay, 2 ampere. Okay, so find the magnetic field at this position, 3, 12, and negative 4. 3, 12, negative 4, maybe somewhere here. Okay, so for this case, okay, you have to apply the formulas, okay, that is for the finite line, even though it is semi-infinite, because we need to figure out the angle, right? So it's better that you apply this formula for the finite line. So you have 4 pi r, then we have cos alpha 2 minus cos alpha 1, and also phi. Okay, I is given, you need to find the r, but before you find the r, you need to define what is your point T. Okay, what is your point T? So your point T will be along the axis y. So your x is 0, okay, as well as your z is also 0. So for the y is following your observation point, which is 12. Okay, so let's find this. Okay, 3, 12, negative 4, minus 0, 12, 0. Okay, So you have 3, 0, and -4. Okay, so for your R. Okay, and then your magnitude, okay, the length will be 9 plus 16. Okay, 25, so it's 5. And the R is equals to, okay, you can write down this one over 5. Okay, so you get the R. Now it's about the alpha 2 and also alpha 1. Okay, so I will draw the y-axis, right? So this is your y-axis. Okay, so might be here I want to draw using my x-axis. Okay, so the coordinate of the observation point is 3, 12, and -4, right? Okay, so 3 and 12 is here. Okay, say that. Okay, and this one is your things, right? So where is your point T? Okay, point T. Where is your point T? Okay, your point T is here, right? Okay, point T. Right. Okay, so this point is infinity, infinity. And this is point A, and this is point B. Okay, point A and point B. So if we join them, okay, it will be like this. Okay, so where is alpha 1? This is alpha 1, and this is alpha 2. So for infinity, alpha 2 will be approximate to 0. It will be very, very small. Okay, and now you need to find what is your alpha 1. Okay, so you can get this angle first, right? So I'm going to use tangents. Tangent 180 minus alpha 1 is equals to opposite. Opposite is 5. So adjacent, so this is 12, right? Okay, 12. So is 5 over 12, right? Okay, so arctangent 5 over 12. Okay, so my angle is, let me change it. Okay, when you get the angle, you have to minus 180. So it's 157.38. Okay, 157.38. Okay, so now we can plug it in. I is 2 ampere over 4 pi r is 5. Then we have cos alpha 2. Alpha 2 is 0 minus cos alpha 1 is 157.38. Okay, and the phi is equals to the dl. dl is following the direction of the current, so it's negative y. Okay, cross with the r. Okay, so the r in this case is 3 over 5x plus, okay, minus 4 over 5z, right? Okay, it's coming from here. Okay, so let's do this. So I will bring this thing inside, okay, inside here. Okay, get 0.013. Okay, cos 0 minus cos 157.38. Okay, 1.92. Okay, so I have 3. So yx, you get negative z. Negative z become positive z. Okay, negative, negative, positive. So here you have plus 4x. Okay, 4x. So we can combine. Okay, mark it. Z plus 0.1 x. Okay, so this is the magnetic field. Okay, at that positions. Okay, I make a mistake here, which is these calculations. Let me correct it. It's milli. 6.37 milli. Milli. Okay, so let's combine again. 6.37. $36.7. Okay, and then 48.92. Okay, milliampere. Right, so this is the answer. Okay, so let's look at question E. You have two infinite and parallel filamentary currents, okay, and they are separated by a distance of 20 cm. Okay, so you can roughly draw this. Okay, so two wires. Okay, by a distance of 20 cm. 20 cm is 0.2 meter. Okay, carry current 5 ampere in opposite directions, so you can label the currents opposite directions. Okay, along the y-axis, so this is the y-axis. Okay, y-axis. So calculate the magnetic force per unit length on the current filaments that lies on the y-axis. Okay, so I think you just need to calculate the force acting on one of the current filament because they will be the same. Okay, they will be the same, and we assume that this is the I1. We want to calculate the force that is acting on I1. Okay, so the force acting on I1 is equals to integrate I1 DAL, okay, and then cross product with B2. Okay, so the B2 is the magnetic flux density that is generated by the I2, that is generated by the I2. Okay, so we can calculate the B2 first. Okay, so B2. Okay, so B2 is equals to mu naught H2. Okay, so for the H2 is the magnetic field. Okay, so you can use the Ampere's law to find the magnitude of the magnetic field. So it is 2 pi r and also phi. Okay, so in this case, this is I2. Okay, and this is the distance. Okay, so let's find it. So the B2 is equals to, you can combine. Okay, you can combine, is equals to mu naught. Okay, 5 over 2 pi r. Okay, so I will talk more about this r. Okay, r is the distance, okay, between the I1 and also the I2. Okay, so now you want to evaluate, okay, your magnetic field at the positions of I2. So this one, the r will be in these directions. Okay, will be in this direction, means that it will be in negative y directions. Okay, negative y directions. Okay, right, so here mu naught 5 2 pi, this is 0.2, and this one is rho l dl. So in this case, okay, your current for the I2 is in the negative y directions, and it cross product with your r, right? Cross product with your r, remember? Okay, so this is your d phi, this is your phi. Okay, so your r is in the, for example, you assume it to be in the No, this is not negative y. You assume it to be a negative x. You assume to be negative x, negative x. Okay, so yx, you get negative z. Okay, you get negative z. Alright, so what will be the value? So 5 over okay, so it will be 5 negative 6 so this one, okay, this one 5 negative 6. Okay, so now we are going to replace it into our equation for the F1. So F1, you have I1, right? So I1 is equals to 2. Okay, and the length is dy. And cross product with 5, negative 6. Okay, negative z directions. Okay, so the length, you can represent it with one variable, that is L. Okay, that is L. Alright, so this one you have 2L. We can combine. You can combine. Is 10, okay, mu multiplied with the L. So this is yzx negative x. Okay, so if the force adding on the divide by the L, okay, force per unit length, so it will be 10, okay, in the negative x directions. Oh, sorry, the current is not 2, the current is 5, okay, the current is 5, so it's 25, so it's 25. Okay, so Newton. Okay, I missed one thing. Here I should write a y showing the directions of the current I1. Okay, then only you can get this negative z.